Okay, so I'd like to begin today. Yes, I'm sorry. I'm sorry, yes, administrative questions. Oh, actually, that's an important point. So one administrative item I forgot to put up here relates to the extra credit on problem set 3. I sent out an announcement on VSpace and via email yesterday saying you didn't have to turn it in. We'll make it do with problem set 4 because we didn't have this in documentation we thought we had on VSpace, but we screwed up and didn't have it there. Hillary asks a question, which is, what are you supposed to do with this? The answer is you're supposed to run a regression. There's lots of ways to do that. One would be to use Excel. That's not a very good tool for regression analysis, but it works. If you're looking for software packages to do this, I like R. You can use Excel if you're familiar with that. You can also use Stata. I'm not a fan of Stata, but if you're familiar with it, that's fine. I think the first I said is R. Yeah. If you've never heard of a regression before, probably this is not the time to learn. It is extra credit for the reason that I sort of don't expect everyone to have grasped those skills. If you'd like to know what a regression is, and it's a very useful sort of tool to have in your toolkit, I strongly recommend taking EAP 118, which is a course in applied econometrics that we offer the EAP graduate centers. That offers a wide variety of really nice tools for analyzing data and relating them to the kinds of models we're discussing in this class. Okay. All right. So let's other administrative questions. Yes. Oh, let's see. I should have that for you. It's something, I don't have the chapters of his books memorized. Something like chapters 2, 3, and possibly 4, depending on whether you're using Perloff or Nicholson, is the material we're sort of in. Yeah, we're still doing consumer demand, and yes, it's the first few chapters of those two books. All right, other questions? All right, let's get started. So this is a not very good, I suppose, a woodblock print of Ernst Engel, who was an important early user of data. We were just talking about regressions. Engel was one of the first economists to really use what we call microdata or microeconometric data to analyze behavior. So he used data collected by some other people. It was an expenditure survey of working class households in Belgium. So the nature of the data wasn't so different from what we collected, what you guys recorded. You kept sort of a diary of your expenditures, and a bunch of working class Belgian families did the same. In this case, back in the 19th century, though. Engel's analysis of these data led him to formulate two laws, and here's a statement of both of them. So the thing before the first period is often called, if somebody says just Engel's law, they're talking about this part here. Here's a statement of it. The poorer the family, the greater proportion of its total expenditure that must be devoted to the provision of food. Okay, so that's a statement of Engel's law. And that law doesn't come from some deep mathematical property of consumer demand or anything like that. It's an empirical observation based on the budget studies he was doing. It turns out to hold up extremely well, though, in a variety of data sets. We'll take a look at a couple later in the lecture. So this is called Engel's law, sometimes Engel's first law. The second thing after the dots is sometimes called Engel's second law. The second law states the proportion of expenditures used for food, other things being equal, is the best measure of the material standard of living. Okay, so the idea here is a simple one, and it's one that's used in contemporary economic analysis. It's that if you look at a household's expenditures, and you see that one household is spending 70% of its income of its expenditures on food, and another household is spending 50%, then it's reasonable to infer that the second household is better off than the first household. And the sort of rationale behind that is Engel's first law, that is the poorer the family, the greater the proportion of its total expenditure that has to be devoted to food. So if you see a household spending a lot of food, you infer that they're pretty poor. If you see them spending relatively little, perhaps you can infer that they're relatively rich. Now, everyone sort of agrees with Engel's first law as an empirical observation. It's extremely robust. That's sort of all the empirical evidence we have in economics. There's some stuff which is just always kind of true. One is that when prices go up, demand goes down. Another is that total household expenditures increase, food share declines. It seems to be true, again, not for any obvious fundamental reason, but empirically, wherever we look, and at whatever level we look, whether it's the level of an individual or a household or a village or a country, this inverse relationship between food shares and total expenditures seems to hold up. Okay, so that's Engel. And this is the Engel who gave his name to the Engel curve, which you guys have already encountered. All right, let's go on. I'm going to come back to Engel in a little bit. Yes, thanks. Okay, so I'm going to begin today with a couple little technical things, and then we're going to turn our attention to some applications and analysis. So here's an important definition that you may or may not have encountered before. You may have seen this before. I want to talk about elasticities, which we're going to begin working with quite a bit. So what's an elasticity? Well, let me give you sort of a motive for it, first of all. An elasticity is a way of measuring the magnitude of change in a variable which avoids units. So when we've been working with things like Engel curves or demand curves previously, it seems like the slope of the demand curve or the slope of the Engel curve depend on the units in which we're measuring the goods. So, and that's sort of an undesirable feature if you want to compare demand curves or Engel curves across different populations or times or prices or whatever. So what we're going to try to do is come up with a way of measuring how responsive something like a demand curve is to changes in prices in a way which is dimensionless. Okay, so here's the trick. You may have encountered this in other contexts as well. What we're going to do is define elasticity, and one way of expressing elasticity in words is just to say that the elasticity of a variable or a function, let's say a variable x, with respect to a variable y, is the percentage change in x. So notice that when we change this into percentages, we've gotten rid of units. So it's the percentage change in x occasioned by a percentage change in y. Okay, so that's one way of putting it in words. So we put things in percentages, get rid of units. Here's some different formulas for elasticity. So let me talk about them just a little bit. So one way of doing this, I guess I should say this capital Greek letter delta. Can somebody tell me what that means? So yeah, we use that to indicate the change or just the difference. So if you have an observation of x at one period, an observation of x at another period, or a change on the graph, that's just the difference between the two values of x. This percentage difference is just that. It's supposed to be the percentage change in x divided by the percentage change in y. Now this is what we do for a discrete change. I'm going to put the screen up again here, with apologies to the right-hand side of the room. So if we have a graph, we put y on this axis and x on this axis, that looks something like that, for example. If we have a discrete change in y, we might call this y, we might call this point y prime. This gives rise or gives occasion, as we said in that definition, to some value of x and some value of x prime. Then we might define the change in x to be equal to x prime minus x, the change in y to be y prime minus y. We define the percent change in x to be something like x prime minus x all divided by x, and the percent change in y similarly to be something like y prime minus y all over y. Okay, so this is what we use for a formula we might use to compute the elasticity for a discrete change in x and y. This is sometimes called the formula for the arc elasticity because it measures really, as you can probably see, something related to the slope of this line. Yeah, sometimes called the arc elasticity. Okay, here's the second one, which is often very useful. If we have a discrete change, one way to get an approximation of that thing is to look at the change in the logarithm of x divided by y. So I'll just throw that out there. Here is an exact formula for a very small change, or the elasticity of point, the point elasticity. This one's kind of interesting, and we'll see it a lot. It's the partial derivative of f with respect to y multiplied times y divided by x. Okay, so I'm going to draw that one over here as well again. So let's take this point here and consider what the elasticity is at this point. What this tells us is it's going to involve the partial derivative of x with respect to y. So of course that's just the slope of this function at a point. But then we're going to multiply it times y over x. So that's a little bit funny. That's going to relate this thing to the slope of a line that passes through the origin and comes to the point. The slope of this thing is equal to, the rise is just, of course, x prime over y prime here. So what we're really doing is taking the partial derivative at this point and then dividing that partial derivative by the slope of a ray that passes from the origin and comes to that point. Okay, so geometrically, that's what's going on. That is the effect of canceling out all the units here and giving us a dimensionless way of thinking about what the slope of this function is here. Okay, here's another way of expressing exactly the same thing. If you mess around with this a little bit, you'll be able to see that this is, in fact, identical to this one. But we say the partial derivative of the log of x with respect to the log of y. That's another expression for the point elasticity, or the change in x when there's an infinitesimal change in y. Okay, so those are all the definitions. Any questions about this? We're going to use this shortly in examples, perhaps. Okay, you're all very silent, which is either good news or bad. Okay, so I'm going to talk about a particular kind of elasticity now, and we'll relate that in a moment to angle curves. I'm going to talk about income elasticities of demand functions. So what is an income elasticity? The income elasticity is the answer to the question, if income increases by x%, then by what percent does demand increase? Okay, so that's the definition of demand elasticity. We've been working in our examples with utility functions, which are often homothetic. We'll call that definition from last time, I hope. For homothetic functions, income elasticities are very boring. They're always equal to 1. So if you get a 1% increase in income, you'll always have an elasticity of 1. You get exactly a 1% increase in demand for the good we're talking about. So that's useful, but not a very interesting quantity. Okay, let's see. We can talk about homogeneity or homotheticity before, so I'm going to skip past that. Here's a fact that this slide you saw a version of last time, so it's just a definition of homotheticity along with an example. Let me tell you about something that relates angle curves and homothetic utility functions. Here it is. If a utility function is homothetic, then the angle curves are all going to be linear functions, and they're going to pass through the origin. So here's a picture of some possible angle curves. Here are some example utility functions. You've seen these before, which happen to be homothetic. So and it goes the other way too. If the angle curves for a demand system are linear and pass through the origin, then the utility function that generated those demand curves must be homothetic. Okay, so that's something that connects angle curves to the property of the underlying direct utility function. Okay. All right, who remembers? So who does? Let's see. Maybe I should back up a moment. So who remembers what angle curves are? It hasn't been that long. So what does the angle curve tell us? Yes. That's very good. Thank you. What's your name? Finally. So that's exactly right. So the angle curve is the answer to the question, how does demand change as income changes? And so for this graph, the axes aren't beautiful, but income is on the horizontal axis, demand is on the vertical axis, and for a homothetic utility function, what this tells us is that there's a linear increase in demand as income increases, and that at income of 0, demand is going to be equal to 0. Okay, so those two things. Yes. That's x, I'll say x on the vertical axis rather than on the y-axis. Yeah, so this is y on the horizontal axis and x on the vertical axis, or if you prefer, y on the ordinate and x on the abscissa. Okay. All right, so let's do a special case of this. So let's think about a homothetic utility function. Here's one we've seen before. This is a version of the Cobb-Douglas utility function. So it's x1 to the alpha times x2 to the 1 minus alpha. Prices are p1 and p2, income is 1. So we've already worked out before repeatedly what the Marshallian demands are for this direct utility function. And you guys know that the Marshallian demand for good 1 is just equal to this parameter alpha times income divided by prices. And you also know, because we've talked about it several times now, that this parameter alpha, which sort of tells us something about how much the person likes good 1 versus good 2, this parameter alpha for this utility function looks like an expenditure share. And you can see that we just derived that here. We've got x1 over here. We multiply both sides by p1, divide by y to solve for alpha. You can see that alpha is equal to, what's this on top? It's price times quantity, which we have a special name for that. It's the expenditures on good 1. Yeah. So these are expenditures on this good. And y is equal to total expenditures. We get that from the budget constraint. So this is the share of expenditures on good 1. And the consumer is going to choose x1 so that that share is equal to alpha. So we'll call this alpha, the expenditure share, sometimes when we have preferences that look like this. Okay. Any questions about that? All right. Okay. I think I mentioned quasi-homotheticity last time. I'm going to return to it for a moment because it's going to be important for thinking about Engel's law. So recall that a homothetic function has the property that there's a monotonic transformation of the function so that the transformed function is homogeneous. And I won't remind you what a homogeneous function is. So we have some examples of that. A quasi-homothetic function is a function where there's a transformation that makes it homogeneous, but you get to add a constant. Okay, so let me give you an example. Actually, let me go back and give you this example. So let's look at this example of a homothetic function. So log of x is not homogeneous. Why isn't it homogeneous? Can someone tell me? Oh, you're using this fact we did just a moment ago. But let's go back to the definition of homogeneity. Maybe I should put that up on the board. Let me do that. So let me remind you that homogeneity. We did a bunch of examples of this. I think 1 week ago. Let me remind you though that a homogeneous function has the property that if we take something like f of x and multiply x times a scalar b, then this is going to be equal to how did I do this? To some number a to the l times f of x. I'm sorry, not a to the l, b to the l. No, sorry, it's the in there and I want b here. There we go. The b to the n times f to the x. So this is the definition. If a function satisfies this property for any constant d, we say it's homogeneous. Okay, now the log function doesn't satisfy that. Log of b of x is equal to b plus, I'm sorry, that's not right, it's equal to the log of b plus the log of x, so it clearly doesn't take this form. So log is not a homogeneous function. However, it is homothetic. And the reason it's homothetic is because there's a monotonic transformation which is homogeneous. The monotonic transformation is just just involves exponentiation. So we can see that's homothetic. So this is not homogeneous. But what we can do is take a transformation of this. We can say that e to the log of x is, of course, just equal to x. And the function x is, of course, homogeneous. It trivially satisfies this thing. What's the degree of this homogeneous function? Remember that n is the degree. Who said that? Okay, yeah, so the degree is, I still didn't hear who it was, but the degree is 1. If we plug this thing in here for f, then n is just 1 for this thing to be satisfied. Okay. All right, so where are we? So I've reminded you what homogeneity is. We were just talking about homotheticity. Now, quasi-homotheticity is what we need here, and I'll stop dragging you through this technical detail in a moment, but it's actually important for what's going to come next. So a quasi-homothetic function looks like this. So here's a function, log of x plus a constant, 2 in this case. So we already know that log of x is not homogeneous, but it is homothetic. Log of x2 is not homothetic. The reason is because if we take this monotonic transformation of that function, what we wind up with is not x, but x plus 2. Now, x plus 2 as a function is not homogeneous. If you multiply that by a constant, if we multiply x by a constant, it's not going to satisfy this restriction. But we say that it is quasi-homothetic because if we take a monotonic transformation like this and then to subtract or add a constant, we can get a homogeneous function. In this case, what we do is we exponentiate. That's a monotonic transformation. Then we subtract a constant 2, and then the resulting thing is homogeneous. Okay. All right, so I hope that's clear. Okay, so let me tell you one more thing about quasi-homothetic functions. I'm going to relate these to the angle curves, and this is why this is important. A utility function is quasi-homothetic if and only if its angle curves are linear, and that's it. They don't have to pass through the origin. So in this case, I've got some quasi-homothetic utility functions. You can verify that they're quasi-homothetic yourself. There's no transformation. If there's no monotonic transformation of this or this, that gives you a homogeneous function. But it gives you something that's homogeneous if you subtract a constant or add a constant to it. Okay, so the property we're after here is that if a utility function is quasi-homothetic, its angle curves are linear, they need not pass through the origin. In the example here, they're going to pass through the number 1 on the vertical axis here. Okay, so is that clear? Okay, now this is important when we think about demand for food. So I'm coming back to Engel's law here now. When we think about demand for food, even a very poor person can't spend nothing on food because they'd starve to death. So let's go ahead and think about that case. So I want to devise a utility function that involves the possibility of starvation. And here it is. So let's define a utility function u of x1, x2. It's going to look very much like what we've done before. The only difference is that instead of having alpha log x1, we're going to have alpha log x1 minus psi. And so psi, this Greek letter psi here, has an interpretation of being a subsistence or a starvation level. What would happen? Think about this utility function for a moment. Suppose that you had somebody who chose or who had a consumption bundle that involved less x1 than psi. So suppose that you had half of psi for x1. What would happen to the utility function? Well, let's see. So x1 minus psi would be negative. What happens when we take a log of a negative number? Yeah, we get a complex result. And we'd like to avoid that. We like our utility functions to be real numbers instead of complex numbers. The interpretation we put on that is that you die. You have to have at least psi or else you're dead. And if you're dead, you get an imaginary utility. That's fine. So anyway, so the interpretation here is if you want to remain alive, you have to have x1 at least as large, actually larger, strictly larger than psi, because log of psi is also not such a pretty number. Or log of 0 is rather. Okay, so here's a way to model this thing. So the idea is you have to have at least psi units of food to survive. You also derive utility from consumption of x2, which might be clothing or something like that, or other goods. And in this case, so this is, you saw from this example a moment ago, this is one of the examples basically, we're going to have a quasi-homothetic utility function. The angle curves aren't necessarily going to pass through the origin. And in particular, what we'll get, you can work this out yourself, I'm sure, is a Marshallian demand function that looks like this. So we'll have x1 equal to psi plus alpha times y over p1. So this is just a simple generalization of the Marshallian demands we've been working with in our examples, where psi would be equal to 0. You can see that this is a slightly more general case. So here, your demand for x1, think of it as food, is you start off by getting psi units. That's what you need to survive. And then you have kind of a normal Marshallian demand for the goods that involves this alpha, this income and prices and so on. All right, is that sort of clear? You guys will buy sort of clear. Very good. Okay, so let me go ahead and relate this to some angle curves that you guys have some familiarity with. So last week you turned in your expenditure diaries. Thank you very much. And with the gallant help of some people who volunteered to do the data entry, thank you, gentlemen. We got this data entered, and I'm going to share some angle curves with you here in a moment. So we're going to estimate those things. It'll involves least squares regression, like we were talking about with respect to the extra credit at the beginning of class. What I'm going to do is take the Marshallian demand, which is this thing, and notice that, remember that we can think about the angle curve as the function that we observe when we vary y but hold prices fixed. Okay? Yes?
Sorry, but I forget. Did you know exactly angle curve? Is that different than Marshallian?
Okay, let me talk about that. So this is just an expression. You can see it's just a Marshallian demand curve. The Marshallian demand curve. So it depends in general on y and on p1. Here I say it's the angle curve because I'm talking about angle curves. It takes the same form. It's just a matter of interpretation. For the angle curve, we're going to hold p1 fixed and vary y. So we also get this thing as a function of p1 if we hold y fixed. So to interpret